A very warm welcome to all of you from Study Hub Sri Lanka. If you've been following along with our Grade 12 Physics Electronics series, you've already tackled semiconductors, diodes, and transistors. You've put in the work, and today we're taking that next massive leap forward.
But before we jump in, I want you to just think about something for a second. How on earth is it possible to fit over 1,000,000 transistors, 1,000,000, into a tiny little space smaller than your thumbnail? I mean, really think about that. The answer is the key to pretty much all of our modern technology. So let's find it.
Okay, here's our game plan for today. We'll start with the IC revolution, how we got from these giant circuits to tiny chips. Then we'll meet the star of the show, the op-amp. After that, we'll look at a little problem called saturation, figure out how to tame the amplifier with feedback, and finally, I'll give you the 2 golden rules that'll let you solve just about any op-amp circuit you see. So let's kick things off with the IC revolution. Just imagine trying to build, say, your smartphone by hand, soldering every single transistor, every resistor, one by one. You'd end up with a machine the size of a car, it would break all the time, and it would cost a fortune. That was not going to work for the future.
And the solution was the integrated circuit, or IC. The genius idea here was to stop building circuits piece by piece. Instead, why not build the entire circuit, all the transistors, diodes, resistors, everything, all at once on a single tiny slice of silicon? This, right here, changed absolutely everything.
Now, what's really fascinating is that not all ICs are the same. We actually classify them by how jam-packed they are. You start with small-scale integration, or SSI, which has less than 100 components. Then you move up through medium and large-scale, all the way to very large-scale integration, VLSI, which crams in more than 10,000 components. That chip in your phone we were talking about? Oh yeah, that's deep, deep into VLSI territory.
The advantages were just mind-blowing. Suddenly, circuits were incredibly small, super light, way cheaper to make, and a whole lot more reliable. But they're not perfect. There are some things you just can't really build onto a tiny chip, like really big resistors or bulky capacitors, or things with coils like inductors and transformers. For those components, you still have to connect them on the outside.
Okay, now let's zoom in on one of the most important ICs ever made. Seriously, this thing is a legend. We're talking about the operational amplifier, or op-amp for short. You can pretty much think of it as the Swiss Army knife of analog electronics. It does so many things. So what is it? Well, at its heart, an op-amp is a voltage amplifier with super high gain, and it has 2 inputs. And the name, operational amplifier, that actually comes from the old days of analog computers, where these were used to perform mathematical operations, like adding, subtracting, stuff like that. Pretty neat piece of history, right?
Now, those 2 inputs are everything. You'll see one marked with a minus sign. That's the inverting input. If you put a signal in here, the output signal gets flipped completely upside down. It's 180 degrees out of phase. The other input with the plus sign is the non-inverting input. A signal here gets amplified, but it stays right side up in the same phase. This simple difference is what makes the op-amp so incredibly versatile.
All right, now we need to talk about the op-amp's most famous feature, which, at first glance, seems like a massive problem. It's all about its incredible power and this idea of saturation.
See, if you just take an op-amp as is, with nothing connecting the output back to the input, we say it's in an open loop state. And in this state, its power to amplify is, well, it's not just big. It is enormous, almost ridiculously big.
Just how big are we talking? Well, a classic op-amp, like the famous MU-A741, has a typical open-loop voltage gain of about 100,000. Yeah, 100,000. That means any tiny little difference in voltage between its inputs gets multiplied by 100,000 at the output.
And that enormous gain leads to a big issue called saturation. Just think it through. With a gain that high, even a microvolt of difference at the input would tell the output to swing to hundreds of volts. But it can't do that. The output can never go higher than its own power supply voltage. So what does it do? It just slams into the maximum positive or negative voltage and gets stuck there. It saturates. At this point, it's not really amplifying anymore. It's just acting like a switch that's either all the way on or all the way off. So how do we fix this? How do we take this wild, super powerful amplifier and turn it into something we can actually control and use? Well, the answer is one of the most powerful ideas in all of electronics: The solution is this really beautiful idea called negative feedback. It's like putting a governor on an engine to keep it from running out of control. We create what's called a closed loop by taking a little bit of the output signal and feeding it back to the inverting input. This feedback signal basically cancels out some of the input, which tames that crazy high gain and brings it down to a level that's predictable, stable, and incredibly useful. So, here's the magic part. When we use negative feedback and the op-amp is behaving nicely, we can use two simple golden rules to figure out what any circuit is doing. Seriously, if you remember these two rules, you're golden. Rule 1. The op-amp will do whatever it can to make the voltages at its two inputs equal. And Rule 2. Absolutely no current flows into the inputs. That's it. Let's see how they work. Okay, enough with the theory. How do these golden rules actually help us solve our real circuit? Let's put them into practice and see what happens. Let's look at maybe the most common op-amp circuit there is, the inverting amplifier. Just like the name says, it takes an input signal, it amplifies it, and it inverts it, flips it upside down. And the best part is, the gain is no longer 100,000. It's set by two simple resistors that we get to choose. And this is just a perfect example of how to use our rules. Let's just walk through it. First, golden rule I. We see the positive input is tied to ground, so it's at 0 volts. That means the op-amp forces the negative input to also be at 0 volts. We call this a virtual earth. Now for rule 2. No current flows into the input terminal. So any current coming through that first resistor, R, can't go into the op-amp. It has to go through the other resistor, RF. If we write that out using Ohm's law and do a little bit of algebra, we end up with this beautifully simple formula. The gain is just negative RF divided by R. That's it. You are in complete control of the circuit. And the other basic circuit you'll see all the time is the non-inverting amplifier. This time, the input signal goes into the positive terminal. The output is amplified, but it stays in phase. And again, the gain is set by those two resistors, with the formula now being 1 plus the ratio of RF over R. You'll notice the gain here is always 1 or bigger. All right, let's just do a quick wrap-up of the key ideas here. First, integrated circuits, or ICs, completely changed the game by putting whole circuits onto one chip. The op-amp is one of the most useful and versatile of those ICs. Left on its own, its open-loop gain is so massive that it just saturates. But we can tame that gain using negative feedback, which makes the op-amp incredibly useful. And finally, those two golden rules are your secret weapon for figuring out how these circuits work. And to finish up, I want to leave you with a question to think about. We've spent all this time learning how to stop the op-amp from saturating so we can use it as an amplifier. But what if? What if we used that saturation on purpose? How could we use those two very distinct states, that high voltage on and that low voltage off, to represent information or to make decisions? That question right there is the perfect bridge to our very next topic, logic circuits. Thanks for joining this explainer from Study Hub Sri Lanka, and we'll see you in the next session.